In this video, we're going to examine the history of the atom. And that goes all the way back to ancient Greece, thousands of years ago, and a philosopher called Democritus. Democritus argued that if you took a rock, for example, and broke that up into smaller and smaller pieces, you would eventually reach a piece that you could no longer break apart. He called that piece the atomos. That means indivisible in Greek. So Democritus envisioned that if you had a piece of tape, that the atom that makes up that tape would be different than an atom that makes up a pencil, or an atom that makes up a marker, or an atom that makes up a piece of wood, that every individual item was made up of its own individual atoms, that the atoms that make up you are different than the atoms that make up me. Now, Democritus, of course, was not correct 100% there, but he did come up with the idea that atoms might exist. Fast forward a few thousand years to 1806 or thereabouts. In England, a scientist named John Dalton was working with newly discovered gases, and he noticed that if you analyze compounds that are made of the same elements, different gaseous compounds, like, for example, nitrogen monoxide or dinitrogen tetroxide, that you could see that no matter what the compound is, there would be a very specific whole number ratio of elements that made up that compound. And he reasoned that there must be whole particles as a result of that. Now, he had some evidence to back that up, and being the first person with evidence of this, he's credited as the person to discover the atom. So Dalton envisioned that atoms were hard balls of matter, and that an atom of hydrogen was different than an atom of oxygen, for example, but you could combine hydrogen and oxygen, and when they connect to each other, or what we now know as chemically bond to each other, you would get a compound, and that compound could be water. But you could also combine hydrogen and oxygen in a different ratio and make another type of a compound, for example, hydrogen peroxide. So Dalton had some things that were correct in his theory. Of course, there were some things that were incorrect. He doesn't describe a nucleus, and he doesn't describe any subatomic particles at all. So let's move forward about 80 or 90 years so to 1890. Another English guy named J.J. Thomson was using a negatively charged electric plate and having electrons jump off of that electric plate and attract to a positively charged electrode. Now, negatively charged electrodes are called cathodes, and positively charged electrodes are called anodes. And if you put the cathode and anode inside of a vacuum tube, so a glass cylinder where the gas has largely been evacuated out of it, the electrons will jump from the cathode to the anode, from the negative plate to the positive. And when they do that, we call that a cathode ray. Now, initially, scientists were looking at that and thinking that they were looking at a beam of electrons, but Thomson showed that you could affect that beam with an external magnet, so it in fact must have charge to it. He envisioned that the atom must have positive and negative charges, and he described his model of the atom as a plum pudding model. Now, that's a British thing. In the United States, that's not a big thing for us. We eat blueberry muffins more commonly, so we call it a blueberry muffin model here in the States. So you can envision that in Thomson's model, it's a big blob of positive. That would be the muffin, and the blueberries would be the electrons interspersed within that muffin. And the electrons could leave one muffin and go across and go to another one. So Thomson doesn't have a nucleus in his model. And we can see that as we go from one model to the next and continue on, we get better and better versions of the atom. And also, we see that there are scientists from all around the world that have contributed to this, and scientists from all different decades throughout history that have contributed to this. Each one depending on better and better technology and better understanding of nature to be able to make their discoveries. Now, Thomson had to have an understanding of electricity to use cathode rays. The next big advancement was the discovery of the nucleus, which was done by a New Zealander, Ernest Rutherford, who studied in Edinburgh, Scotland. And what he did was discover the nucleus. And what Rutherford did was interpret what's called the gold foil experiment. Interestingly, he didn't set up this experiment, but the people that did weren't really making correct interpretations. So what you do is you take a radioactive piece of polonium. Now, polonium had been described, or discovered rather, by Marie and Pierre Curie, and Marie Curie is from Poland, so it's named after her home country. Polonium gives off positively charged radioactive particles. They're referred to as alpha particles. I'm going to represent them with these plus charges here. They come out of the box, and the box is made of lead, so the rest of the polonium is contained there. There are no alpha particles going anywhere else, they're only coming out that hole. But that would be very much like water shooting out of a garden hose without a nozzle on it, kind of spraying out in a not very focused stream. So you can kind of make a nozzle here, if you will, by putting a lead plate in front of that, a lead disc, and putting a tiny hole in that disc. So based on the size of the particles, the loss of mass of the polonium, and the size of the hole in the disc, you could calculate how many particles would be coming through that hole in the disc. So essentially what we have here is a particle gun. So we take those alpha particles and we aim them at a piece of gold foil, because you can make gold very pure and very thin. Now, they were expecting that they were essentially shooting bullets at blueberry muffins. And what would you expect to happen? Well, if you put a detector screen around this, such that when a charged particle hits it, the detector screen gives off a little spark, you could see that the particles were doing pretty much what you'd expect. They'd hit the screen, the alpha particles would go through the atoms making up the gold foil and hit the screen, just like bullets would go through blueberry muffins. But very unexpectedly, in fact, it only happened about 1 out of every 20,000 particles hitting the gold, a particle would bounce backwards. Now, the two people running this experiment thought that was an anomalous result and didn't pay attention to that. But Rutherford said, no, that was very, very important. In fact, he did some calculations and said, well, we can make a few conclusions here. If the positively charged particle is bouncing back, it must be hitting something that's also positively charged. And when it hits it, it bounces backwards. Now, this is a very energetic, fast-moving particle, so when it hits that and this doesn't move, it means this must be very massive. And you can do some calculations to calculate that. In fact, more than 99% of the mass of the atom must be located in this spot. He called it the nucleus. The word nucleus means kernel or seed in Latin, just like you'd see seeds at the center of an apple. Now, not only must it be positive and very massive, it must be really, really tiny, because most of the particles that we're shooting at it are missing. They might deflect a little bit if they get close, but for the most part, these particles are missing it. Only 1 out of 20,000 bounces backwards. So we're kind of stepping through the looking glass here a little bit, saying that atoms must be made of mostly empty space, with almost all of the mass in that little point in the nucleus. In fact, if you make the atom as big as a stadium, the nucleus would only be as big as a grape within that stadium. So this is at a time when cowboys were still on the range in the United States. At the turn of the century, people weren't really driving in automobiles very much. We hadn't flown the first plane yet. And here this guy comes out and says that atoms are mostly empty space. That means that most of everything around us is made of these negative force fields, and that's kind of quite a statement to make way back then. Even now, that seems like kind of an odd thing to say. But it's a testament to our understanding of nature scientifically, that if the evidence points us in that direction, that's the way we go. So the next breakthrough has to do with, the next model of the atom has to do with describing where electrons are outside the nucleus. And this was done by a scientist from Denmark named Niels Bohr. So Bohr studied the bright lines that were given off as you energize atoms and came up with the idea that electrons must be moving around the nucleus of the atom like planets move around the sun. Now this is called the planetary model, and you might say, hold on now, the planets travel around the sun kind of on the same plane, and these are all on different planes. So it doesn't really perfectly match the way planets are moving around in our solar system, but it's kind of a romantic idea that the electrons moving around a nucleus would be similar to planets moving around a star. If we were to flatten it out, we could see a little bit more of how that might match up. Now, if the nucleus is at the center, these would be different energy levels, and I'm going to do my best here to draw these energy levels in more tightly packed orbits as we go around. And I'm going to stop at 4 orbits here. So we see energy level 1, energy level 2, energy level 3, energy level 4, and so on. So energy level 5 would be very tight there, energy level 6, energy level 7. We'd get almost a fuzzy boundary there as we get to the end. Now this is what Bohr did. And in fact, I probably really shouldn't even draw a nucleus here at all, because any nucleus that I draw is really going to be too large to scale, right? If we made this as big as a stadium, and that would only be as big as a grape, there's no way I could draw a small enough speck for anybody to see it. So let's just kind of exaggerate that nucleus and make it a little bit bigger. Understanding that that's an exaggerated scale there. If we represent an electron with an E-, and you put some heat or some other energy source into the atom, the way the atom absorbs that energy is the electron would move farther away from the nucleus. We say it would go from its normal position or its ground state to an excited state. But it would be unstable in that excited state, so it would fall back down, and when it fell back down, it would release a certain amount of energy that would manifest itself as a bright line of light. Now that bright line would have a very specific wavelength, a very specific frequency, a very specific energy. And there would be several bright lines that would be produced from electrons falling down from all different positions. In fact, electrons could fall down from higher energy levels back down to the first energy level, or the second, or the third, and so on. So we would get a lot of different bright lines that were being produced here. Now there are 7 energy levels that we have discovered in an atom. So if you look at a hydrogen atom that has only 1 electron, you get lots and lots of bright lines that can be explained with orbits just like this. Now Bohr did a pretty good amount of math to describe all this. And it turns out that that works great to describe an atom like hydrogen that has only 1 electron. But if you take an atom larger than that with more electrons, even an atom like helium that has 2 electrons, the number of bright lines that get produced cannot be explained by just using orbits. So very early on, Bohr understood that this model was too simple, that we needed to have a more complex understanding of the atom. But what this did introduce to us is that, in fact, atoms do have energy levels, and electrons are actually leaping by disappearing from one position and reappearing in another position. They're not gradually moving out or back closer to the nucleus. The electrons are actually just disappearing and reappearing, jumping in a package of space. Now, the word quantum means package in Latin. So the electron disappearing from one spot and reappearing from another spot, producing that bright line of light when it drops back down from a higher energy level to a lower energy level, is called a quantum leap. And this is called quantum mechanics, because we're talking about package movement of electrons. So Bohr actually discovered a new type of physics. That's not the way that Newton would describe things moving. If you see a baseball moving through space, the baseball seems to continuously move through space. If it falls down from your hand to the ground, the baseball would slowly release energy, or you could say gain kinetic energy as gravity accelerates it. But it would happen very gradually. And here we're not seeing that. We're seeing the electron just, boom, release all the energy all at once. So quantum mechanics is something that we don't necessarily observe directly in everyday life, but it does affect all of the physics that we use now for materials and power and telecommunications and so on. We have yet to find an example of where quantum mechanics fails us. And yet it's another step into the bizarre that not only are atoms made of mostly empty space, electrons are moving in ways that we normally don't see things moving in our everyday world. In the next video, we're going to take a look at more depth into quantum mechanics.